Okay, so thank you for the invitation. It's a pleasure to be here. And yeah, the title is Nairian Models. Every time I hear Zoltan speak, I feel guilty because last time I heard him speak, then I started calling my theorems that haven't been finished as conjectures. Now he gave this wonderful introduction to Borel equivalence relations, and I am not going to do that. So I'm not going to introduce the subject. Sorry about that. Okay, so.
People are complaining that you're not loud enough.
Okay, so I have.
But is this even working? Did you turn it on?
Is it working?
I think no. Is it?
I think you have to put it higher.
Or maybe higher, yes. Just speak into it and let's see.
Is it working now?
I think it's better.
Yes? Okay, good. Okay, so let me, I will try to give you some picture, but not define all the basic notions. Okay, so theta is that's pretty basic. Yeah? So theta is a supremum of all the ordinals that are surjective image of the reals. And theta regular is the theory ZF plus ADR plus theta is a regular cardinal. And okay, so this is, this slide will have two motivational theorems. And of course, the first one is Wooden's theorem that you can force MM plus C over the model of determinacy. If you start with ADR plus theta regular, that's the MM model. And we've seen this theorem yesterday in NAM's talk. The other one is the CH model. So you can force with the col omega 1 of R and get this, of course, CH will be true, but then you'll get there is an omega 1 tensor ideal on omega 1. So there are these two very interesting possibilities you can go from determinacy. The question is if you could generalize this, yeah?
Sorry. What is the point of this?
Oh, add 1 omega, sorry, it's add 1 omega 3. Should be add a coin subset to omega 3. Well, I didn't spot that.
Call omega 1R and then add one subset.
It should be omega 2. In the first one should be omega 3, in the second one should be omega. Sorry. Oh, okay, so the first typo was on the first page. You always check when it's. Okay. All right. I spotted other typos, but not that one. So in the MM model, you have theta is omega 3. In the CH model, you have theta is omega 2. So what do I, in general, mean the MM model? You'll start with Pmax at a coin subset to omega 3, which is your theta, and then you'll do some forcing above. Now, in Wooden's case, you didn't do any forcing. That was enough. But you'll do some forcing, which is omega 4 closed, which means you don't add subsets of omega 3. Now, in the CH model, you'll start with the col omega 1R, add 1 omega 2. So you did what, yeah, in Wooden's case, you didn't need the Q because they already had a choice. And then maybe you have to do something above. Okay, so this is what I mean by the MM model and the CH model. So the basic question is, can MM++ hold in the MM model? And then you can ask, can every uncountable regular cardinal carry dense ideal in the CH model? I'm not really sure what dense ideal means, because I think there are competing definitions of what that should mean. But I will, if there is time, I will state something at the end. Okay.
What is the MM model?
Sorry. The MM model is you start with Pmax, you add a coin subset to omega 3. That's the, and then you do something above.
So the question is over some V that satisfies AD.
Yes.
You're speculating.
Can you say again?
You don't have such a model. You start with an AD.
No, I mean, these are confusing. So the MM model is when you start with Pmax and then you add a coin subset to omega 3. Then you have MMC. We're always thinking of models of determinacy. Yes, so we're calling it the MM model and hoping to get MM inside the MM model. Look, there's nothing wrong with the formalism. It's just maybe how am I supposed to go back? This is very confusing. Okay. So the MM model is one that you will start with the model of some determinacy model. you will force with Pmax, add a coin subset to omega 3, and then maybe you will do something else. Okay? That's what I call the MM model. It doesn't mean that MM holds in there. So can MM++ hold in the MM model? Okay. All right, but if maybe you're not going to get MM, so maybe you'll try to get one of these consequences, right? As a test question, can you have any of the consequences? So just leave it on for a few seconds. Okay. So as a test question, right? Okay, for square, not square omega 2, that's the first one that you would need a little bit more than C, yeah, to get. Some years ago, there was a square meeting in which we were able to get failure of square omega 2, but that was a model of the form L of P of R. Maybe you need it a little bit more. But it was not a big model.
You had the square meeting to get the failure.
Yes. So I have to make, yeah, okay. So this gave at least me hope that maybe it's possible. All right, so to get anything more in the MM model, we need to discover determinacy models with a structure above the theta. In fact, what's going on? That remark is important. If you want to go beyond, because MM just MMC plus will already give you power set of R sharp and etc. So you need to discover structure above theta if you want to go beyond. Okay, but what should that be? Okay, so HOT sub X is, of course, the set of hereditary ordinal definable sets where you are allowed to use parameters from X. HOT is just HOT the empty set, and the Nairian model is this. So you cut HOT at beta, and you construct with up to gamma. And the Nairian model at gamma is that. Now that's a bit confusing. That's not exactly what I mean. If you just really follow Gödel's constructibility, this would have more ordinals than gamma. But what I mean is that rearrange the construction in a way that this would actually have exactly, the ordinals of this structure would be gamma. So you have to do, like, feed in the countable sequences as you go. Yeah?
What do you mean by power?
Like V gamma of HOT. Okay, so we also have these two other models, which in the first one you put the entire L on top, and the second one you put HOT. Now there's no reason why this should be interesting, right? In V, why would this be any interesting? And so they are interesting in models of determinacy. Okay, so I have to give you some definitions. Now we are assuming AD. Kappa is OD inaccessible if take an ordinal less than kappa, you cannot subject power set of alpha onto kappa. Okay, just the definition seems to be pretty straightforward. Okay, if you assume AD, then delta alpha is the collection of sets of reals whose wage rank is less than alpha, right? So to take a set, you look at all the continuous preimages and close on the complements. And that gives you a rank. Under AD, wage order is well-founded, so each set has a wage rank, and you look at all those that you get before alpha. Okay, so you can think of it as like V alpha, really, in the model of determinacy. Yeah. Okay, so then I need this Suslin notion of Suslin cardinal. A set is kappa Suslin if it's a projection of a tree on kappa, and then we say it's kappa is a Suslin cardinal. If you have a set which is kappa Suslin, but it cannot be Suslin for some lambda less than kappa. Okay, so it's the first place. You know your set is Suslin, and you go look where the first place you can find where you have this tree witnessing it. Now, Suslin cardinals are very important in determinacy. This is the places where new sigma 1 facts become true. But I just needed to make the definition meaningful. The LSA cardinal is a Solovay cardinal, so it's inaccessible, OD inaccessible. And then we have this little thing. If you look at the supremum of the inaccessible, all these inaccessible cardinals below, yeah, so that will be the largest Suslin below delta, and then it will be less than delta. So it cannot be limit of such cardinals, and for some determinacy reasons, that will also end up being the largest Suslin. Okay, that's what an LSA cardinal is. What is LSA? LSA is largely sustained axiom, which basically says theta is an LSA cardinal. Okay, so that's just some definitions to just make it formally accessible. Okay, so let's say delta is a Nairian cardinal if the Nairian model at delta is a model of ZF. Okay? And we say delta is a full Nairian cardinal if it's a Nairian cardinal and also solvable, so it's an inaccessible, or the inaccessible cardinal. Okay? Now there is a wonderful theorem by Steele and Wooden. Forget HPC. I'm not going to tell you what it is. It's just some hypothesis. So if you assume HPC, which is the inner model theory, part of all of these, and that also delta is an LSA cardinal, which is a limit of Wooden cardinals in HUD, right? Oh, also remember that this is AD plus is everywhere, yeah? We are always in the model of AD plus, not in the model of ZFs. Then delta is a full Nairian cardinal, okay? So it makes sense. It's a nice ZF model. Okay, well, you have ZF, but does it mean it's nice, right? Can you do anything with it? Okay, so just remember that the Nairian model of delta is you take HUD up to delta, like V delta of HUD, you add countable sequences, and you construct up to delta, and then if you make these assumptions, then it ends up being a model of ZF. Okay, so can you make any use of Nairian models? Assume AD plus, so this is generalizing the theorem I stated earlier in the square meeting. So assume AD plus and HPC. HPC is always going to be there. And suppose delta is a full Nairian cardinal. And now we look at theta of n delta. Now, remember, n was built inside the determinacy model, so it's a model of determinacy because it was built inside. Okay, so it has its own theta. And then we look at the successors of theta. Now, pick an n, look at the Nairian model of these kappa n's, right? Now take the poset, which is the MM model, right? If you were just doing Pmax add 1 kappa 0, that's how you start building the MM model. And then you do the rest. Why do you do the rest? If you don't do the rest, you will not force choice, right? So if you go back to the definition of MM model, this should make sense. You have to do, if you build bigger models of determinacy and you want to force Pmax and then add coin subset to omega 3, there's still more stuff to well order. And that's why you need to add the other coin subset. Okay, so G is n generic, then you get failure of square at each kappa I. And then you get kappa I is omega 2 plus I, right? So you get kappa 0 is omega 3. Oof. 3 plus I. That should be, I guess, this should be omega 3 plus I. Yeah? So kappa 0 is omega 3, kappa 1 is omega 4, kappa 2 is omega 5, and etc. If I'm going fast, please ask me to slow down. Okay, so you get this at the successors of omega n. Of course, that's a consequence of mm plus plus C plus C plus plus C plus plus plus, right? So this is towards getting more Martin's max. Now then, recently we also had the following. Assume AD plus, and suppose now delta is a Nairian cardinal. You don't have to assume it's the full one, just any. And take psi. Now I could say, instead of writing all of that psi is the least Nairian cardinal, but that might have put psi somewhere else than where I want. So you take delta a Nairian cardinal, and then you take psi, which is the least inaccessible cardinal of HUD, that is a limit of less than strong cardinals. Now, you don't have to worry about that particular, yeah. Just what we will end up having is that psi is the least, if you're familiar with determinacy, there's just these windows where LSA stuff happens and delta is a Nairian cardinal. Now we take the least Nairian cardinal in that window. But that is what it will be, yeah? Okay, so we now look at the Nairian model at Xi. Then we do Pmax. So we go to the MM model where we force with, okay, so what is Q? Q is going to add coin subset to every cardinal. And it has to be full support iteration, right? Okay, then you take the generic, you force. Yes. So you take the generic. No, the conditions. Well, but it factors nicely, right? So you can cut at some point and look at the.
It's the direct limit of all the poles.
Yes, yes. Okay, so what you end up having is the square fails everywhere. Okay.
It's up to the least inaccessible.
N is the Nairian model at Xi.
Yeah, so it doesn't have any inaccessibles, right?
It does not have any inaccessible.
Full support sense. Better.
Once it's least inaccessible, that's the limit.
Okay. I'm sorry? Can you say? I cannot hear what. No, well, that that is the whole point of. That's a very good. You know, we only have DC. So how are you going to prove that you don't collapse cardinals? This is a very good question. In fact, it's the key question.
So is it true that
I cannot really hear. I think so, yeah. Otherwise, it will not be countably complete, right?
So you have no inaccessible.
No, there are no inaccessibles. Yes, it's all.
So just backward east without inaccessible.
Okay, it's just. Yes.
you can't get through inaccessibles by doing backward east right now?
But as Hugh will point out at some point, it is very hard to get large cardinals in this model. So, okay, let's go on. At the moment, there will be Nairian cardinals with inaccessible cardinals. We know that they exist, but I don't know how to force choice over them. Okay, so it's all right. Okay. So the hypothesis of the previous theorem is weaker than a Woodin cardinal that is a limit of Woodin cardinals. What hypothesis? Oof. The hypothesis that there is a delta which is an Nairian cardinal and etc. Yeah, that hypothesis is weaker than a Woodin cardinal that's a limit of Woodin cardinals. And then as a corollary, you of course get that this is a weaker theory than Woodin limit of Woodin cardinals. And I should have shoot. I wanted to ask people which one is what is the hard, but I guess I told you. So the hard part, the hard part is you might think that proving that square fails is the hard part, but that's actually quite okay. We already had the format of that in the square meeting. The hard part is proving is forcing choice. MM++ C, it's just Woodin's theorem, right? So there's nothing new there. Okay, so how? I feel like because it was a bit unexpected, at least to me, I want to tell you the proof rather than go on and tell you more science fiction, right? So the proof will be a proof of this. So we start with the Nairian cardinal. We look at that. We do the Pmax and then add coin subset to cardinals, and we want to see that ZFC holds, right? That's the thing we want to do. Okay, so first of all, you cannot. This kind of becomes exercise in trying to force choice over models of ZF. Okay, so you can't always do that, of course, but there are cases when you can do. Of course, Usuba developed some techniques. Woodin has, of course, the forcing over Reinhardt cardinals and things. And so we are doing something similar to, I think, what Usuba is doing with these Lonem-Skolem cardinals, but unfortunately, I think they're collapsing cardinals when we are adding coin subsets. We don't want to collapse cardinals. It will be a total mess if you collapse cardinals. Okay, so we need to be more careful. And you can think of DC kappa if you're not familiar with that. that will be the principle that allows you to prove if you do closed enough forcing, you don't add a subset to kappa. So if you do kappa closed forcing, then you don't add new subsets of kappa. Yeah. Okay. So let me explain to you how we force choice in the simpler case where we were just looking with the successors. Yeah. I don't know if I'm going fast or not faster. Okay. So Gabe says it's. So you start with a Nairian cardinal. We have kappa 0 is the theta. Kappa I plus 1 is kappa I plus of n delta. So these are going to be omega 3, omega 4, omega 5, and etc. And then n is n plus kappa 1, right? So it's just basically here the question is how do you know that power set of omega 3 is well ordered, right? Because kappa 1 is omega 4, kappa 0 is omega 3. The question is how you know that power set of kappa 0 is, well, I mean, and also y is omega 1, omega 2, omega 3, omega 4, why are kappa 0, kappa 1, why are they cardinals in the extension? That is the main. So we need DC. Okay, so that's n is the Nairian model. Well, this plus version of the Nairian model. And then we want to see that if I just force with Pmax followed by Cohen to omega 3 followed by Cohen at omega 4, then that would be a model of ZFC. Well, I mean, the deeper problem is why kappa 0 and kappa 1 are cardinals, right? Not just that it's a model of ZFC. Okay, so keep that question in mind. I guess I didn't. The way it's written, it doesn't specify. That's the difficult part. So to demonstrate the idea, I will just tell you how DC omega 2 is proved, right? So why is it enough to prove DC omega 2 in G0 star G1? Because we know already by Udin's work on Pmax, right? That G0 star G1, G0 was Pmax, and we know that's nice. G1 is adding a Cohen subset to omega 3. We already kind of know that that's nice. Now, if you prove DC omega 2, that will prove that omega 3 is not collapsed, right? That kappa 1 is not collapsed to kappa 0. I keep saying omega 3, omega. You have kappa 1, which is going to be omega 3. We have omega 4. We have kappa 0, which is going to be omega 3. Then it's omega 2. Everything here will be collapsed to omega 2. This is the true omega 2 of V, yeah? And omega 1. The first two posets well order this much. Everything that has hereditary size. I mean, you have a well ordering of H kappa 0 basically, H omega 3. But now we need to well order subsets of omega 3 and not collapse omega 4. And we are in a model of ZF, which is otherwise it's obvious, right? DC omega 2 would say I can make omega 2 many choices. So if my poset is omega 3 closed, I make omega 2 choices. And then I take the union. That's a condition that will, yeah. So this will be enough to prove.
So it's not for analyzing add?
Yes. Yes. Add this one. Oh, but that's not my fault. We want to see that this forcing does not collapse omega 4 to omega 3. Now, if you're not in a ZF model, that's obvious. But you only know that this is omega 3 closed. Oh, I put omega 2. Okay. Well, you can also ask why this forcing doesn't collapse omega 3 to omega 2, for example. That is also not clear, right? If you have DC omega 2, you can do that. Okay. So thank you, Gabe. So the key point is to try reflection, right? You pick a relation on kappa 1 omega, this one. Okay. Then we reduce it. So this is a relation that's a thing of the name, the forcing relation. Yeah. Now we find some alpha here. such that R restricted to alpha to the omega is omega 2 closed. But now alpha has size kappa 0, so I can push this to some s on kappa 0 omega, right? So in fact, you have a function from here to here. Because alpha is of size kappa 0. And now I'm reflecting s again, so I can find now some beta such that s is omega 2 closed. Right, so you start with your R, which was on kappa 1 to the omega, and that's enough because everything is built from counterbalancing. So you take your kappa 1 to the omega, you reflect down to alpha to the omega. Now that's of size kappa 0, you reflect to kappa, you just push it down to kappa 0, then you reflect again, and then you use the magic theorem that was improved. This omega 2 we know is true in this portion of the universe. So I know I can take my thread, right? I can take a thread through here. That will be thread through S, because this is just restriction. And then I push by F. So I get my thread. Okay? So it's this, the reason it works is because I can reflect. Now you could say, wait a minute, if this was not a regular cardinal, you couldn't do it, right? But it is a regular cardinal. Okay, so that's just a simple reflection which allows us to do it. Yes, otherwise how you find which is this?
Right. So you're proving this.
I need that this is omega 2 closed. So if it had cofinality, if it had small cofinality, how would you make sure that you could just find something?
Part of the reflection shows that kappa 1 is regular.
No, you prove it already before. So before I start all of this proof.
You already have kappa 1.
Yeah.
In the force.
In the ground model. So you have this fact. If kappa is actually strongly regular cardinal, if I pick beta less than kappa I, there is no cofinite map from beta to the omega onto kappa I. This is in N, not in V. And of course, the key takeaway is the reflection, that I could do this reflection. Okay, so what we do in the more general case, and assuming I'm going at the okay speed. So you start with the Nairian cardinal, right? Now we take the least inaccessible cardinal of heart, which is a limit of less than delta strong cardinals. Again, that's just going to be the least cardinal with the least Nairian cardinal in this window that you pick, this LSA window you pick. Okay, so we now do Pmax followed by the full support iteration that adds a single coin subset to every cardinal greater than omega 2, and then we take a generic. So that's the setup. Oops. That is the setup. We are going to work in the Nairian model at XVIII. Oh, I guess I didn't say it. Right? So we are going to work at the Nairian model at XVIII, not delta. Let me say why I keep writing delta instead of the XVIII. Because if you just write XVIII, it seems the theorems are only about that small initial segment. But you can take full Nairian models, and it will be true for their small initial segment. Right? So while the forcing is nice, we only have DC to begin with. So how can we show DC omega 1 holds? Of course, that was the point. And you can no longer drop down at limit stages. Right? So if we let kappa omega, so now we go, how does this work? So now we have kappa 0, kappa 1, kappa omega, right? This is the soup. So we would like to see that if I do the forcing here, so this will be adding coin subset to each one and then taking a limit with full support. So if you don't prove that, then we don't know that the rest of the posets, your omega 2 is down here. How would you prove that omega 2 is not collapsed? right? Okay, but we can no longer reduce, if I take a relation on these, now this is unfortunate, it's a subscript that is a power, yeah? But if you take some relation on it, how am I supposed to reduce to anything below? I can't do that. Okay, so we have to find some other reflection, and here is a reflection that I think will do. So reflecting below kappa 0. What this means is that it's kind of like, I think it's very similar to Usuba's Sloan-Skolem principles. So basically what it's saying is that if you take a Rankinish segment of V, right? Remember n beta, we can think of n beta as the Rankinish segment of your Nairian model at beta. Okay, so you take that, then you find something below kappa 0, and an embedding from that into n beta. But the key point, I guess, would be the ones that are useful is, well, I guess all three. Everything is key. Okay? So that's kind of what we need. We need to create this picture down there. And you can already see why. Because if I want to prove DC omega 1 for these, right? I reflect down below kappa 0, and I already had DC there by Wooden's theorem. So I take the thread there and push up. Okay, so we say lambda is a true cardinal of n if for some set x, lambda is theta of x to the omega. What that means is lambda is the sup of alpha, which are surjective image of lambda to the omega. Yeah. I should have said that all of these kappa i's are true cardinals, so they just happen to be successors of each other. Okay. So if it's a true cardinal, then you have this reflection. But unfortunately, I'm going to lie a bit, and I'm sure you will catch my lie. It's not going to be enough, right? But it's easier for me to illustrate what's going on. Am I going too fast? Can I? People who follow can. Okay. Right. So we take lambda. Now we want to show that I can reflect. I can create this kind of.
So is the problem with just reflection in true cardinals doesn't give you DC omega 1?
No, I think you don't. You should reflect here, not below kappa. You should reflect below kappa 1 or kappa 2. Because what you need to know is that not just omega 1 closed in V, but omega 1 closed in the generic extension. And so I think you need to reflect here to make it work. Yes, this reflection holds for any two pairs of true cardinals. I cannot hear, sorry.
It's just like in the successor case, you reflect the same.
Well, yeah, but it's much harder to put. So this is easier. This is where the ideas are simpler. So we take omega 2 close relation and get sigma. So I'm just trying to explain why we have this omega 1, which I already did actually, in this fake way, yeah? So we reflect, we imagine this kappa omega plus 1 was your cardinal. You take a relation which lives in this portion. You collapse it below kappa 0. And then we take a thread for the inverse of R, which we know exists. But you could already see there is something going on with the names, the forcing, yeah, exactly where does the relation live. We want to prove the relation, the DC omega 2 in the forcing extension, we cannot prove in B. It has to be, okay, so there is a name for this relation and etc. Okay, but that's the sort of the template. But you can make it work with, if you reflect it down here, you can make it work. Because if you reflect down here, what you could guarantee is that the whole will be closed on the, not just omega 1 sequences, but functions from kappa 0 omega onto the whole. That's key.
So kappa 2 is what, omega 5?
Omega 3, omega 4, yeah. Mm-hmm. You need your think, because Pmax is of size the reals. You need it to be closed under functions from reals. So you need to reflect somewhere here.
You're using what you inductively shown
Yes. DC, yes, exactly. Okay, so how are we going to prove that this type of reflection holds? Again, here is some data, which is probably hard to digest, so let me draw a picture. This is where the inner model theory comes in. Delta is a Nairian cardinal, psi is, again, this other thing. Right, so this is going to be my HUD. Yeah, I take lambda, my kappa 0 is down here. I take kappa, and this is psi. And also I have two Woodins here. There's the lambda, there is the kappa. There are these two Woodins. There is the delta. These guys are strong to delta. Right, the psi is somewhere here, but its role is, it's technical for me to explain what the role of this psi is, but it just says something about this kappa. Never mind. Okay, so now what we do is we look at, because remember I'm assuming HPC holds, right? So I have a hot pair, P sigma, and I can assume that all of these guys have preimages. All of these guys have preimages in P. Okay, so that's the setup. I have my HUD. This is in HUD. This is the picture in HUD. And that's the picture in P. And then we have the iteration embedding from here. Pi P infinity is the iteration embedding from P to HUD. So now we look at the local Nairian model at kappa P. Right, so now let's zoom in into P. We have lambda P, we have kappa P. Here, because there is a connection between the determinacy world and the internal derived models of the HUD mice. In P, I can kind of discuss what the Nairian models are, and I can look at the derived model at kappa P and form sort of the local Nairian model. And what exactly is that? Well, we look at the direct limit of all iterates of P up to kappa. Kappa P should be kappa P there. This should be kappa P. Yeah, of length, again, kappa P. And then we add all countable sequence. So this is going to be L, this zeta, HP to the omega. But where do we compute these countable sequences? In the symmetric collapse of kappa P. Okay, and zeta is the ordinal height of this HP. Okay, now look at, this is the MP plus. Now we look at where lambda P goes into this local limit, right? And my MP is going to be NP plus restricted to gamma. Gamma O. It should have been gamma P. So please think of that as gamma P, because it's defined inside P. So here we have gamma P. Okay, now we are going to define, no, that is okay, that is gamma. That's not defined in P, that's the direct limit. What is gamma? Gamma is I'm looking P up to here and checking where lambda P goes to. This is not, we look at P up to here and look at all iterates in V. So this goes to some HUD limit gamma, okay? So that would be below kappa 0. And I want to define this embedding. What is the embedding? Well, we do what we usually do in HUD analysis. We trace back, take an ordinal below gamma, trace back where it comes from, and then do what? And then shoot by the bigger limit. So any ordinal below gamma, tau, I can get a pre-image of it by iterating this much, right? But then I can use the full direct limit to shoot it up. Okay. So that's what sigma does. It pulls back points to the local limit and then shoots up with the full limit. Well, it turns out it's a elementary embedding. Now, why does sigma induce mob? Because everything is defined from countable sequences. So if I define sigma on ordinals, that induces embedding on countable. Okay. So I have sigma plus, and sigma plus is elementary. Why is sigma plus elementary? This is, if you're familiar with the ceiling proof that uses iteration trees, that's what we want to do. Then we go to the last line. It's basically, this is the whole point. This local Nairian model can be realized as the Nairian model at gamma and as the Nairian model at n lambda. Both of them, right? Remember, n gamma is sitting somewhere down there, and lambda is sitting somewhere higher up. And you have this countable version of both of them. You can do some genericity iteration to realize that little thing np as this one and as this one. Okay?
Why do you need two quadrants, U0 and U1?
There's a technical reason for that. Because I need to form this genericity iteration, you need to keep making sets of reals generic. And that's where they're used.
So you're using U0 or?
Both of them, U0 and U1. You need to do genericity iteration, so that you need to have woodens somewhere. Ooh. Okay, so I don't know if I convinced you that this is elementary, but because this little thing, if you're familiar with like derived model type of theorems, then right, you say something is true if and only if it's true in the derived model of the countable thing, but then the countable thing can be realized as as both this and this. So the thing that was true here is true in NP, and therefore it's also true here. Okay. All right, so that's why sigma plus is elementary.
But you don't have a direct.
Sorry?
You will not have a direct elementary embedding of n gamma into n lambda.
What does it direct mean? We have some, so.
But you're not really pulling back the P, right? You're pulling back the same thing past P that picks up.
Yes, yeah. I will even have longer thingy. Okay, let me go on. Omega 2 is super compact. This is kind of if you hear forcing people, they will always tell you omega 2 is a super compact. Now I know why. If you assume 80 plus and delta is an Nairian cardinal, by the same reflection, right, that I was explaining to you, we have n lambda and we reflect it to n gamma. This allows us to prove that this model is closed under omega 1 sequences, for example. Because if I have an omega 1 sequence down here, I can just push it up by that embedding. Okay, so it's the same argument tells me that they are closed. But then there is a theorem of Baker and Jackson, which actually says that in the determinacy model, omega 2 is super compact. So if you find an inner model which is closed under omega 1 sequences, and it's closed under ordinal definability, it will have the super compactness measure. Right, so you'll have that the Nairian model is a model of ZF plus omega 2 is super compact. Okay, should ring the bell for people who are doing MM.
So the closure is omega theta and T.
No, there's a bigger determinacy model around. There is this big V. In this V, we have the super compactness measure on P omega 1 cap gamma, but that's the same here, and it's ordinal definable.
I see. Okay, so it's
Omega 2.
you close all the way up.
Yes.
Just the number. Not your fault.
I will state the problem at the end, which addresses that point of view. Okay, so you get omega 2 super. You also get any Suslin cardinal is super compact in their successor, but I don't know if people care about that. By the way, you also get omega 1 is super compact. I just never hear forcing people say that. So a commercial break. So there are other consequences, which if you go to Doug's talk, you will hear about them. But I don't mean don't go to Tom's talk. This is. Oh, great. So Doug is just speaking on his own?
No, there's someone else that
Oh. This is not an anti-commercial break for. Sorry. So if you want to hear about some consequences on hot conjecture, SRP, and other, there's some other things that we can do. So let me try to say some few words about the CH model. Now we were discussing this 2 years ago. We don't have it as a written up theorem, so that's why I call it conjecture, following Zoltan's suggestion. Okay, so the CH model, remember you're forcing with call omega 1 R first, right? So you enumerate reals length omega 1. Then you get omega 1 is generically super compact. In fact, what that means is this. If I collapse any regular cardinal to be countable, right, I'll get a generic embedding with critical point omega 1, M is omega closed, and that's it, yeah. So I don't know if this is the definition of dense ideal on kappa. I think you want to collapse it to the predecessor. At least that's what Yair and Monroe got, but you get this version. Okay, so if you collapse kappa to be countable, it's a direct generalization of Hughes' theorem. In Hughes' case, you were collapsing omega 1 to be omega, and you were getting the generic embedding, which sends omega 1 to omega 2. Okay, now you take any kappa regular, collapse to omega, you get the generic embedding. That does that. Okay. And the V is the CH model. So, kappa plus, yeah, but that's isn't that? I thought it follows because. Yeah. So this slide has an open-ended question ended up in 4. So I mean, what is the Nairian model of V? Yeah, why do we always have to go to the determinacy model? Can we do it in V? I thought a lot about it. I don't know, but maybe the chunk model that Obrad was talking about, the chunk plus model, maybe that's a Nairian model. Now, what does it mean to be? I guess the question is, can you force, say, failure of square everywhere over this model? I guess that would be a test question. Yeah. And the other question that I think a lot about is, if you can, so that's Gabe's point, there are too many symbols. Well, maybe there is a theory that removes all of this inner model theory and all the symbols, right? Now, it shouldn't be the compactness theorem. Don't just take a finite set of, yeah, I mean, something that's nice, right? A simple axiomatization of Nairian models that, just like AD does with L of R, and then you develop Pmax theory, yeah. And then the other question is whether you can have axiom star kappa for all cardinals kappa, right? So this would talk about omega 4, omega 5. And then the other one is if you can have 2 to the omega 1 equals omega, of course you can have that in some generic extension of, right? But whether you can have interesting things, for example, the tree property at omega 3 and 2, omega 2 and omega 3. To the omega 1. So like I'm thinking of the tree property on omega 3 here, right? Well, you could force with Pmax and then make to the omega 1, omega 3, but you didn't create any structure. So for example, could you get the tree property at omega 3? Could you have Rado's conjecture, things like that?
Starting from a model.
Yes. Right? I think I forgot to put a thank you slide, but that's it. Thank you.
questions?
So you always talk about no inaccessibles when you do the forcing. What breaks when you do have inaccessibles?
Well, what happens is, well, first of all, I don't know what that, or the least inaccessible, the psi in the full Nairian model is of cofinality omega. So that's definitely not the least inaccessible. I think if you go to the least inaccessible, then the strong cardinals, you'll have strong limits of strong, even strong reflecting strongs. You know, in V, these kappa i's, these guys, any of these that are below psi, right? Below psi, any of these kappas are of size kappa in the determinacy model. I think if you look at the first inaccessible, that would be V cardinal. I'm suspecting, I don't know who has anything. And then you get a lot of overlapped extenders, and this has always been a problem for the model theory. Well, not even that. Even analyzing the regularity of these successor cardinals, I don't know much about that. But we are working on it. So a nice thing would be to solve 2 and then not do inner model theory. Right.
Yes.
Is this working? Do you have a guess for what the consistency strength for a full Nairian model is relative to Wooden limit of Woodens?
That's a very good question. Mahler Wooden, I would say, in hot mouse.
I'm sorry?
Mahler Wooden in a hot mouse, maybe.
Oh, so much stronger.
I think so, yeah. Well, I think it's definitely stronger than Wooden limit of Woodens, yeah. Yes. I mean, it could be even, I think it's Mahler Wooden, but it could overshoot everything, right?
Okay, so let's thank Grigor again.